So September 14th, 2015, silence spoke. And what I mean by that was, first of all, we detected gravitational waves. That was the first time that we had a piece of data confirming Einstein's theory and prediction of gravitational waves. 100 years after the prediction, we discovered the gravitational waves. And it's analogous to something I'm working with. So I also teach yoga, and often I teach one-on-one with people. There's a person I'm working with right now who has ringing in her ears, tinnitus. And when she first came, I had a plan, what we were going to do. And I said, look, this is going to sound like mumbo jumbo, garbage at first, but this is what we're going to do. I'm going to teach you to listen to the silence behind the noise. She knows me well, so she trusted me. And I gave her some practical things that she can start to work on. And eventually, recently, actually, a couple months ago, she messaged me, and she had an event with her hearing, and she said, I'm listening to the silence behind the noise. So part of that therapy, it reminds me of this concept of detecting gravitational waves as opposed to all the other ways we've understood the universe to this point. So this is an image of how we understand the universe now. So everything we've ever detected is essentially noise arising out of space-time. Noise in the sense that it's not in the fabric itself, but some activity within or interacting, but not arising from the fabric. So everything we've measured, all of these great instruments and telescopes, has been using some aspect of light, whether visible light or to the extremes. Or we've even detected particles, which again is stuff, is noise on the fabric of space-time. So now with gravitational waves, we've detected the silence behind all that noise, the foundation where these things have arisen from. So the Nobel Prize last year went to 3 people who worked on this detection, namely Kip Thorne, Barry Barish, and Rainer Weiss. And I'll talk a little bit about each of their contributions to this. So what they detected were 2 black holes coalescing around each other and merging. When this happened, it created a chirp, a huge wave in space-time. And this is what we detected. So 2 black holes, as they turn, they distort the fabric of space-time, sending out these waves. As they come closer and closer and eventually merge with one giant energetic wave, and then they become one. So 2 masses orbiting around each other produces these gravitational waves. Once we have a symmetric object like a sphere, it doesn't produce the waves anymore. So the final collision, the burst of energy, and then no more waves. So what happens when a gravitational wave moves through something? So this is a very simplistic expression of this, but it captures what's most important here. So we have the Earth over here, just normally sitting there. We have a sort of red wave, which doesn't come up very well in this slide. As a gravitational wave moves through, it has the effect of stretching an object in one direction, which leads to compressing it in the other direction. And as it continues to move, it stretches in the opposite direction. So it's actually like a spheroidal wave. It compresses and stretches as it moves through space-time. And whatever is in space-time gets stretched and compressed as well. So unlike, for example, light, which can be blocked by something, gravitational waves move through the fabric of space-time itself. It moves everything that's there. And this is an exaggerated image by far, because the actual stretching of the Earth from a gravitational wave passing through it is less than an atomic diameter. So the entire Earth stretches less than the diameter of an atom as the gravitational waves move through it. And this is why Einstein said we will never detect gravitational waves. It's just too precise. It requires too much precision. So this is part of the problem. So the problem with measuring gravitational waves, if you take something like a ruler, as the gravitational waves move through, they have the same effect on the ruler that they have on the Earth. So stretching it from side to side or stretching it up and down as the wave moves through. So the question is, how can we measure gravitational waves as we move through? Well, I want to give credit to Joseph Weber here. So I have my first German physicist. His name is Dieter Forster. If anybody was here for the first talk, he was the crazy German on the bike who was showing time dilation. He's still a good friend of mine from Temple University. And when I told him about this talk, he said, you have to talk about Joseph Weber. So when gravitational waves were detected, the team that detected it and announced it first gave credit to Weber. He's the grandfather of gravitational wave detection, really this entire field, and essentially a quantum hacker. Because if you're trying to detect things that are smaller than the material you're using to detect it, you have to figure out some tricks. And so this was his first try and quite well-known try of detecting gravitational waves. So he was actually nominated for the Nobel Prize because he helped lay the foundation for lasers and masers. Masers are just microwave lasers. And his attempt was something called a Weber bar, which was a giant aluminum cylinder that was designed to resonate as a gravitational wave passed through it. So he had high precision detectors here to look for very, very, very subtle vibrations. And he claimed in 1972 that he detected gravitational waves. And in fact, this prototype was created all over the world. There were many labs that tried to reproduce what he discovered. And unfortunately, physics is not always nice and generous and things like that. So it looks like potentially there was an analysis issue with his data, which led to a false positive. His results were never replicated. And although he believed for quite a long time he really did detect them, nobody else was able to reproduce it. But his work laid the foundation for what came next. Notably, the observatory I'm going to tell you about, LIGO, started around this time. It was actually the early 70s that the idea came to be. And what he also did is he set the standards for extremely high precision measurements. So the many, many students who came out of gravitational detection field, the many PhDs, were primarily about how to find signal in so much noise. It's a noisy, noisy universe, and there's signal in there to be found. So some of his work is even on the moon. He has a gravitational instrument on the moon to detect, to do some experiments on gravity. And he is noted by everybody in the field as the person who really started this attempt, this crazy attempt, to measure gravitational waves. So Ryan Weiss, one of the winners of the prize last year, had the idea of using light as a ruler. And the idea is, if you have some source of light projecting, say here in some cavity with a mirror on one side, the light goes down and comes back. As the gravitational wave moves through and sort of shortens the ruler, the path that the light takes is a little bit shorter. And as the wave continues to move, stretching, the path that the light takes is a little bit longer. And this happens because light is a constant speed. So rulers can change and stretch, but the speed of light is the speed of light. This was one of the crazy things about time dilation. Speed of light is the speed of light, and that has some sort of funny results. But because it is a constant, the light itself doesn't get stretched with gravitational wave movement. And so this was, in the early 70s, he proposed this theory. So if you compare the distance the light traveled on track A versus track B, and you'll see that the light traveled a little bit longer as the wave propagated through and shorter. And if we could measure the differences between these paths of light, we might be able to detect if a gravitational wave has passed through. So this is a very busy slide, but it's from LIGO, so I'm going to use it. So the Nobel Prize was given for the first detection, September 14th, 2015. And a lot of scientists were super, super excited, but sort of people who weren't that into science weren't that excited about it. Still a very exciting thing. And for my own personal connection here, September 14th, 2015 is the 7th birthday of my first child. And from the first talk, the number 7 is quite a lucky number in the history of cosmology. So about 1.3 billion years ago, 2 black holes collided, and a gravitational wave moved out of that collision. LIGO is a large detector, which I'll describe in some detail, which detected this wave passing through. This was almost 100 years exactly since the waves were predicted through the theory of general relativity. And my peripheral connection to the story, one of the reasons it's so close to my heart, is because there is a man named John Wheeler we talked about last year, connected with the Princeton Matterhorn project, developing nuclear weapons for the US, and also developing theories about black holes and compact objects. He had a student named Kip Thorne, who got his PhD in 1967, and shortly after went to Caltech, where he was the youngest faculty member. In the time he arrived there, Virginia Trimble was finishing her PhD. And Trimble was the first woman ever accepted to Caltech on her own merit. They had a policy that women would only be accepted under exceptional circumstances, which usually meant there was some man that they wanted to have there and she was with him so she could come. And as she tells the story, her acceptance letter said something like, "You can come, but we would rather you not." And she came. And as she was finishing her PhD, she was at the process where, in those days, you have a lot of handwritten articles, and to finish the process, you submit these papers to somebody else to type up to process, which can take a few weeks. During that time, I'm going to paraphrase here, Kip basically said, "You want to go look for some black holes with me?" So he gave her a project to do, looking at binary systems, and she discovered a few black holes in her free time, thanks to Kip's suggestion. A couple years later, she moved to University of California, Irvine, and she married Joseph Weber, who was the grandfather of gravitational wave detection. This is an image of Virginia Trimble drawn by Richard Feynman when she was at Caltech. And then many years later, I'm not that old, this black and white photo is only from the 90s. I'm not sure why it's black and white. In 97, when I was a student at Temple University in Philadelphia, somehow I got myself into a research fellowship program at Caltech for one summer. And my second German physicist, Robbie Vogt here, was the director of that program. He was the director of LIGO until very shortly before I arrived. And a fortuitous set of circumstances, namely my advisor, my mentor for that summer, was out of town for a good part of the summer. So Robbie said, "Well, you know who can teach you about LIGO? I'll take you to Kip Thorne." So he dropped me in Kip's office and he gave me notes and notes about LIGO and how it worked. And I just sat listening to these masters of gravitation talk shop sometimes. So it was a really powerful experience for me. And at the end of that, I decided, well, I want to do more physics. This is fun. So what can I do? So instead of applying for jobs in my last year of college, I applied for graduate school. And I asked Kip if he had any suggestions of schools he would recommend. And he said, well, UCI, University of California, Irvine, is pretty good. And Virginia Trimble's there, and she's awesome. So I did a little more research than that, but really not much. Like, I found out that Irvine has an annual average temperature of 74 degrees Celsius, and it's by the beach. So those were my two main factors. And when I got there, Professor Trimble was on my dissertation committee, although I didn't do research with her because she works alone. but she's really the reason I finished and didn't leave early. And so this is a little bit of my sort of science family and people who had a tremendous impact on my life with their generosity and their support.